Hi, everybody. Hope you're doing okay today. So I've been posting most of the homework answers, the solutions. I think I've posted 8 out of the 11. So I'll get a few more today and you'll have all the different solutions. I also posted instructions for the final project. And that I envision some kind of like a 5-page thing. Maybe the first page is a general outline of how you would, list of different like lessons you would do, like a little outline of them. And then the next like 3 pages would be a lesson plan. However, there's no special format for this lesson plan, just something that like I, for instance, would be able to take and go teach your class. Now, if you're not a teacher yet, still you've probably made lesson plans just to show, okay, I would ask this question and I would give this activity. And then the final thing, I'm just going to throw it in as an appendix to your final paper, just to write a little 1-page kind of end of the term reflection. How did this course, did it make you think about things, or how are you going to think about math differently now that you've taken this course? Really, it's up to you to say. Not everyone likes the history of math. I mean, I find it really interesting. You can say whatever you want, but I think it's good to do a final reflection.
Professor, I have a couple of questions.
Yes.
So you said it's due at noon next Thursday, right? Before noon?
Yeah, I think I have to turn in the grades like by 5 o'clock that night. So that's as late as I could accept it.
Okay, and are we going to have a final exam in addition to the final project, or is the final project the final exam?
I might make a final like assignment that has like 1 question from each topic we did, but it would be just like another homework assignment.
Okay.
Like an overall, like a general review, but not a thing that you're supposed to take in any sort of like timed conditions without looking at notes or anything like that.
Okay, and then for the unit plan, how many lessons does it have to consist of?
I think at least 4 lessons, but if you can do it in less than 4 lessons, because the unit you think doesn't, I mean, as far as the outline goes, you're just writing like 1 sentence about each lesson. So really, there is no maximum number of lessons, but I would have at least 2. I would guess you'd want to have like 4 though, but if you could do it with like 2 lessons or 3, that's okay.
Okay, got it. Thank you.
Okay, you're welcome. So yesterday, I had a pretty ambitious lesson, but I made sure that I was going to go nice and carefully and slowly through it. And if I only got through half of it, I would do the other half today. And the thing that I was going to do today, I'm just going to remove from the course, which is fine. There's a lot of history of math, and I had to pick a subset of topics. And one less topic, which was going to be just more stuff about Archimedes proofs. I will refer you to a playlist if you want to learn about that stuff. At the end of the term, I'll give you a playlist of all kinds of more history of math and books and things. Homework. Oh, well, next week there's just going to be there's a new lesson on Monday and on Tuesday, and then there might be 3 lessons next week: Monday, Tuesday, and Wednesday might be like an overview. It may just be 2. I may not do this cumulative assignment at the end, but there'll definitely be at least 2 next week, because we do have 2 more with today's, and then we have Monday and Tuesday with new material. Okay, so let's continue with the 3 problems of antiquity. And as I said, these things are like really, really famous. I'll show you This is on Amazon.com. You can see that last year a book came out. I mean, these problems of antiquity, you could find, they're in like every history of math book talks about them, but I had never seen a single book that's dedicated only to the 3 problems of antiquity. You can see I purchased this book on January 3rd, 2020. I haven't finished reading it. I only read the first few pages. I really want to read it because it's, to me, really interesting that for 2,000 years people worked on these 3 problems. So the only problem of antiquity that we've seen so far has been trisecting the angle. And we've seen 2 ways to do it. Trisect the angle. We saw, here's an angle. We saw the Archimedes approach. Well, they were both Archimedes approaches. That's not a good circle. The first Archimedes approach was to, here's the angle I want to trisect. And it was to locate somehow special point there.
I'm sorry, you're going to want to switch away from your Amazon screen. Thank you.
Thank you. Here we go. So this was the Archimedes approach. Anyone want to refresh our memory? How do we know that F is in the right place? Like, how could I verify what would make F like in the correct place so that this angle is exactly 1/3 of that angle? That's right. FG would have to equal the radius. And that can only happen in one special spot. Any other place you put that F, FG will either be smaller than the radius or bigger than the radius. But if you get it to that special spot, it will trisect the angle. We also saw that angle could be trisected with the Archimedes spiral. So both of these methods involve Archimedes. It's actually not that easy to trisect an acute angle because this piece is so small, but I like to do like obtuse angles because then all I do is trisect this line segment, swing it around, and I trisect the angle that way also. So both of those were due to Archimedes. So we did get to do some Archimedes. But we're not done. We still have 2 more ways to trisect the angle, and then we have 2 ways to square the circle, and 1 way to double the cube. And those are the 5 things I'm doing today. Today will not be a 2-hour, 2.5-hour marathon like yesterday. The next curve I want to introduce you to is called the Quadratrix, Quadratrix of Hippias. In this picture, I have a square, I have a green quarter circle, and then I have this red thing. That red thing, which looks almost like a piece of a parabola or a piece of an ellipse or something like that, that red thing is called the Quadratrix of Hippias. And let me show you how the Quadratrix of Hippias is defined. So in your in the classroom, the Google Classroom, Why is it saying that? Classwork, okay. Discard changes, I don't know what changes they meant. In yesterday's assignment, there's all these videos and then there's the homework, but then there's this link that says Greek geometry. When you click on that, which you can do if you have like another window, if you want to like follow along, it brings up this book, this GeoGebra book. Anyone who's a math, if you're training to be a math teacher, you'll want to experiment with GeoGebra because it's one of the best free tools for math that there is. It's amazing. Anyway, in that book, there's all these different constructions of the stuff. Actually, a lot of it's the stuff that we did. Euclid 1-1, midpoint. I don't see angle bisector. There it is. 1-9 is angle bisector. 1-10 is midpoint. Pythagorean theorem is 147. Book 6, proposition 9 was the dividing a line segment into n pieces. Is Thales' theorem. Okay, but now, where is my quadratrix? Here it is. Okay, now look carefully at this. I'm gonna see if I can go full screen for you because it will. Okay, hope that looks good. Let me get the chat up. Okay, do you see that good? Someone's telling on the chat. Are you looking at a circle with the square? Okay, great.
Yes.
So what I have is a circle with radius BG and this square here. Now, when I move this slider, what you'll see is a radius going from being perfectly like vertical down to being horizontal. And now when I click that line, here it is. Here's the important thing. Two things are happening when I move this slider. Point G is moving clockwise, from A to D. And point C over here is moving down from A to B. And they are moving at the same rate, meaning when G is halfway to D, C is going to be halfway to B. So here C is working its way towards B, G is working its way towards D. And when G is 3/4 of the way, this A is a percent. So when A becomes 0.75, G is 3/4 of the way down from A to D, and C, this horizontal line, has dropped down 75% of the way. And when it gets to 1, they both, if they're racing, it's a tie. C makes it to B at exactly the same time that G makes it to D. Now, when I click this button, you see the curve that is traced out by the intersection of those two line segments. So just get your mind, and you get to, I don't know if you, is it just out of curiosity? Does anybody have this open at the same time as me and they're like fiddling around with it simultaneously? I was curious. Okay, maybe not. That's all right. You can, at your own convenience, fiddle around with it and get a feel for it. The way we make the point move, though, is through this slider. I don't think you could drag these actual points here. You have to move the slider. Okay, and that's a quadratrix. Now let's see some properties of the quadratrix. let me come back to the iPad. So here's a little description, a little bit of how it's being created. Let me go back to here. Here comes a mathematical question for you to think about. If the square has side 12, and I make a point here so that this is 4 from here to here. Here's my question for you. It's kind of a challenging question to think about. My question is, how big is this angle? Take a minute to think about that. And if you can answer this question, you have a really good feel for the Quadratrix. I see someone wrote 30, someone wrote 120. And someone wrote 45. Okay, so we have 3 different answers. Do you agree with one of those 3? Or do you have a different answer? Because it's actually not one of those 3 answers. Anyone have another suggestion? And I see 50 as a possibility, but it's not 50 either. And I see 65. And there I see the correct answer, which is 60. Well, why is it 60? Because 4/12 is 1/3. So this line, the horizontal line, has dropped sort of 1/3 of the way. It's completed 1/3 of its journey, which means this point going this way has completed 1/3 of its journey. This point, sorry, has completed 1/3 of its journey also. So it will have ended up, it's ended up over here. Wait a second. I got myself a little bit confused. Hold on a second. I got myself a little bit confused. It's I see. Sorry about that. Just get rid of this point. It's this point that went 1/3 of its journey. So this is 4 from here to here, which means from here to here was 30 degrees. So what's 30 degrees? That was the first answer, was 30 degrees. 30 degrees is that angle. But the question was not what's that angle. The question was what's this angle. So it's 90 minus. I guess what we're saying is that the answer is going to be 90 minus 4/12 times 90. This piece here was 1/3 of 90. So 1/3 of 90 is how much it went. Yes, it's the complement of 1/3 of 90. So that's why it was 60 and not 30.
Can you explain why that's 30 again?
Yes, it's 30 because if I were to have that little slider, that slider would be at 0.33, which means both lines have moved 1/3 of their progress. So the fact that it's 4 out of 12, we know that's 1/3. But this here also is going to be 1/3 of it's trying to do a 90-degree path. It's trying to get from here down to there this way, but it's only made it 1/3 of the way down. So it made it 30 degrees, which is why this angle is 30 degrees, because this angle relates to this arc here. This angle changes. This angle grows. This one grows from 30 to 90. But the question wasn't about this angle. It was about this angle, which is 90 minus it. Because, and it is similar to yesterday. It's similar to on the spiral of Archimedes. And that's why both of these can be used to trisect. I haven't told you about trisecting the angle yet.
But that's only because the height was 4. If the height changed from 4 to 6, would that still be the case, or would it change to 45?
It would have become 45.
Okay.
They both would have become 45 degrees. And I can also go the other way. I can ask a question where I tell you the angle. And why don't I just do that, just to get like one more thing to mess around with. So let's say that this angle is just 15 degrees. And again, the whole thing is 12. And then my question is, how long is this piece from here to there? Why don't you take a second to think about that? Well, by the way, is this the whole square side again. And yes, I see 3 people said 10, and 2's not bad either, because 2 is sort of the rest, but it was asking for this piece. So basically 75 degrees have happened already. And 75 over 90 is 5/6. So that means that this line has gone 5/6 of its journey from 0 to 12, and 5/6 of 12 is 10. 2's not bad. 2 is this piece here. I like that question. That shows that you have a feel for the quadratrix. See, I have here, it's like a connect the dots, where you go like this. And then the H, it's all presumed that this is all equally spaced. So the H goes from there, and the E goes like that. And then finally, this I, that's the radius. And here's the horizontal line. I'm surprised. So something looks wrong about that. I think on the homework, I don't know if I have you draw one. I can't remember for sure. Well, now I want to show you how you can use a quadratrix to trisect an angle. I'll keep coming back to my, is there a way to clear the whole screen at once? Well, I can make a big eraser. It's not that big. Now you can't actually create a quadratrix. You could create individual points on it, Like if I gave you a square and the quarter circle, I could construct, for instance, a 45-degree angle, and I can make the midpoint. And in doing so, I can get a single point on the quadratrix, and I could like bisect my angle, and then I could take the midpoint and make another, and I could take a midpoint and angle bisector. Using midpoint and angle bisector, I could make as many points as I want on this shape. I could just keep taking midpoints and angle bisectors. I can make as many points as I want as long as I have time. I can't make 1,000,000 points because it would take too long. And I certainly can't make an infinite number of points if that's my goal, because that would take even longer. So in that way, this quadratrix, we can't create it with a composite straight edge. So even if it can be used to trisect an angle, you would need it. And there are actual tools like devices that make this quadratrix. They're really cool looking, like with a sliding thing. Anyway, there are tools to make one, but that would be illegal to use that tool. You wouldn't have accomplished the problem of antiquity because it says you're not allowed to use anything but a composite and straight edge. But yet it is still an interesting curve, the quadratrix. Let me show you now how the quadratrix can be used to trisect an acute angle. So step one, here is the angle that I want to trisect. Step one, make a line segment from here and make it perpendicular to the bottom side of the square. Step two, use the trisecting. You know how we learned how to trisect a line segment? Use it to trisect this line segment, although we don't really need this point, but I'm just showing you that point just so that we see. One of the constructions from 2 classes ago was to divide a line segment into 3 equal pieces. Step 4 is to make a horizontal line from this point here. And step 5 is to connect this point to A. And we'll talk about why this works in a second, but for now, those are the 5 steps. The red line was from where the angle intersected the quadratrix. The green point was 1/3, made it so that from the bottom to the green point was 1/3 of the whole segment. The blue line was just horizontal, and the purple line was just connecting the dots. I will show you in this. Check this out. Trisect here. I'm going to hide that. So here's my angle. And now I'm going to say trisect angle. There it is. There was the work. So as I move this point around, HI was the red line. J was the HI trisected. K was on the horizontal line. And you can see over here, angle DBG is 60.75, angle DBL is 20.25.
Professor Malachi, that A equals 0.33. Where's that reflected?
That's a percent. That's like, that just goes from 0 to 1. So like, that's like, okay, I haven't started yet. Now I'm 100% done. So when it's 0.5, when it's 0.5, the angle is going to be 45 degrees. So this is like a percent complete thing. That's what the A is. So the A is related to what the angle is, but it would take like if I make the A, for instance, 0.33, then you notice how the angle is about 60 degrees, because the A is like, what percent down am I from? So it's not related to what the radius is or anything. I can make the circle smaller or bigger. This is a like percent complete.
Thank you.
You're welcome. What is about BA? Can I see what this is? I forgot. About move A to 1. Oh, that's something else. That's coming later. Okay, let's go back. Yes.
So in trisecting that angle, we're only looking for one of the rays that'll trisect it?
That's right. Yes, we don't have to draw both of them in. So creating an angle, one angle, that's 1/3 of the original. We don't have to literally have three pieces, like have three angles that are all equal to each other that fit together. It wouldn't be too hard to draw the other one over here. Like I could just take the angle bisector. But yes, trisecting an angle, unlike, when we bisect an angle, we cut it into two pieces because that's what happens when you make a bisector. But trisect, you only need one line. So you'll cut it in so that you have 1/3 and then 2/3. So you don't actually have to have three equal pieces. Just one piece that's 1/3 of the original is satisfactory.
Thank you.
That's a good question.
So we're not worrying about two other points to trisect the line.
That's right. If you drew this other point and then did the same thing, made a horizontal line, you would then have three pieces, like a pizza slice cut into three, but we don't need it. Because once you have one, you've kind of accomplished the goal. So trisecting means to create one angle that's 1/3 of another angle, but not literally cut the angle into three pieces and see those three pieces. Kind of like with the spiral of Archimedes yesterday, same thing happened. We just had one angle. And then the Archimedes with the circle and the special F point also just had a single angle. But this one was tempting to want to split it up because it's actually like overlapping, unlike the ones from, actually the Archimedes spiral was overlapping also. Okay, let's see why this works. I think I'm going to use some actual numbers. Might help you see. If the whole thing was 12, and if this is like 8 right now, because it's gone down by 4, so 8's the length of the red line. I'm going to change this, make this, instead of 12, I want to make this 9. I'll make it 9 and 3. So it's still 12. So this is 9, which made this a 60-degree angle. But then when I cut this line in thirds, this piece here is going to be 1/3. That's just going to be 3. And if I imagine that horizontal line, I'm going to draw both of the full horizontal lines. So when this line has been cut by 1/3, the angles also, or the line's been cut, this line is 1/3 of the red line. This angle will be 1/3. And it has to do with the whole, like, the way that the points move, like at the same rate. Like if you move halfway, the other one also moves halfway, because they're both like racing to the bottom, and they start at the top, and when they're halfway, they're both halfway at the same time, and they're both 1/4 of the way at the same time, and they're both 1/8 away from the bottom at the same time. So if you cut one thing in half, the other thing is going to get in half also. The line segment and the angle are proportional. Okay, let me say it that way. So when the line segment is this entire thing, the angle is 90 degrees the angle's 90 degrees at that point. because the angle's like that. But then as it works its way to them both becoming 0, they kind of happen proportionally. And it's very similar to the spiral of Archimedes in that way. Well, that wasn't my greatest explanation. Maybe if you go on to this, you can really convince yourself more of it by dragging this and saying, okay, you know, this is A is 0.6, which makes this thing about 40% of whatever the squares side was. And then when I move this to 0.8, I should probably add to this thing some more measurements, like the measurement of AB. I think that would help you understand it better. But I guess the short answer is the horizontal, this horizontal line, it moves, since it moves at exactly the same rate as that radius BG. When it doubles in the distance it went, or when it gets closer, the other one gets closer in the same way. When I cut this in half, they both get cut in half. The angle and the line segment are proportional to each other. It's not so important that you know that. These proofs for this course, I like to let you know them, and I want them to be things that you think about. But if you're struggling to understand the proof, but you were able to calculate out, you know, the numerical values before when I put them up, I think that's the most important thing. Here's a picture of the trisecting with a quadratrix. Okay.
Okay, so can I ask a question?
Yes.
So on the homework, specifically problem 9, you have a problem similar to this, but I don't think I understand what you're talking about when you say you want to find 3 points and then find 5 more.
Let me take a look at that. I think, let me just look what it says there. I think what I'm asking you to do, let me just look at this to be sure, number 9. Oh, I see. So because they're telling you the lengths are 6 and all those arcs are equal, you can get 3 points easily. So to find 5 more points, you could either take like you could do midpoints of like between any of the 2 points on the A, you know, that A, D, E, F, C lines here. Let me bring up the, put that on the screen. So basically what I'm saying is that there are various ways to get more points. The easiest way is probably to take a midpoint of like CF and then do the angle bisector of GAC and see where those come together. But you could get clever. Like if you want to use a protractor, that would be a cool way to do it also. You could say, well, I'm going to make a 20-degree angle. But the 20-degree angle, that's like, I mean, 70 degrees have passed. So I'm going to make, you know, what is 7/9 of this length. So you could use a ruler for that, and you could make whatever angle you want. I think the easiest way, though, is to use midpoints and angle bisectors. And I'm going to say, hint, the easiest way to do this is with midpoints and angle bisectors. Thanks for asking that question, because it's not that clear from the way it's worded.
All right, thank you.
You're welcome. Okay, well, that was one of the things for today. I have 4 other things for today. So we have 3 different ways already to trisect an angle: spiral of Archimedes, quadratrix of Hippias, and the Archimedes circle construction. But we are going to get 1 more. So we will have 4 ways of trisecting an angle. On a piece of paper, I'm going to show you a new curve with a very exotic name. It's called the Concoid of Nicometes. And here's the way it works. There are three things given to you. There is this, this big horizontal line over here. There's a point, which I'm just going to put over here. It doesn't matter where you put it, but just I'm going to put it there. This point is called the pole. This big horizontal line is called the Directrix. And this random other line there is called the distance. And depending on, the Directrix is just a horizontal line that goes on forever in both directions. But depending on where you put the pole and how big this line segment is, you'll get like a different shaped curve. Now here's how you find points on this concoid. What you do is you pick a point on the Directrix, anywhere you want, and you connect the pole to the Directrix. And now listen very carefully. See this distance up here? You continue that line until this length is the same as that length. And the endpoint of there is a point on the Directrix. So let's just imagine that this was like a 1 inch distance. That would be 1 inch also. The green line, well, that depends on where I put the point. So here, I'm going to make another point. I'm going to pick a green point on the Directrix like that. I go straight towards it. And then when I continue, by the way, is this point going to end up at the same like height as the other one, or is it going to be higher or lower? That's a good thought-provoking question. Is the points on the, by the way, I'm going to make this this point like purple, just so that we have actual, this point's purple. If I make that red line, is the purple point going to be above or below or at exactly the same height as the other one? Yes, it is going to be higher, because it's kind of like, this one's at an angle, this first one, this one's going straight up. And that is another point. And what ends up happening is you get a curve like that. It looks like a bell curve a little bit. Interesting that it never touches the Directrix, because if I were to pick a point way out at the pole, way out on the Directrix, and I were to go towards it, well, I still have to keep going a little bit more to get to the Quadratrix itself. Let me show you the animation of this. In here, we go to Concoid of Nicometes. And I will also go to full screen. It looks nice that way. So you see over here, as I move this point F around, this gives you a really good visual of what's going on. See the 2.25 up here? So that red line is always 2.25. That's the concoid. And just so you know, if the pole was closer, this thing would look like more like a semicircle.
Where is it 2.25?
It's not 2.25 anymore because this line, I changed the size of it. So if I change this, now it's 2.25. So this distance, whatever it is, this other red line will always be the same. So you see how you see that red line? It's like a stick. Like it does not, it moves around, but it doesn't change size ever. That red line doesn't.
Okay.
Now, if I move this down far, it ends up looking, more like a bell curve or something like that. If I put E above it, it ends up upside down. And changing this distance actually has the same effect as moving the pole. If the distance is really big, it starts to look like a circle a bit more. And if it's really small, it starts to look like just a wave. When I picture the Concoid of Nicometes, I picture it to be about this dimensions. Now, sometimes there's this bottom branch. Let me tell you what this thing is. See that loop-de-loop? What that is if I go from E towards F, and then instead of going forward, whatever this CD distance is, I turn around and go backwards that distance, I end up with this loop as the other branch. That loop's actually not very important. It just looks kind of cool, and I wanted to tell you what it was. But I usually only care about the branch that doesn't have the loop on it. But I did want to show you the loop. Oh, was that Nina just asking, what does this do? Well, I'm going to show you this Concoid of Nicometes is going to be another way of trisecting an angle soon. Incidentally, if I move point E farther down, it doesn't make a loop anymore. And if I move it up, it makes a bigger loop. And then it comes upside down. So Nina, for now, I'm first just defining what the Concoid of Nicometes is, so we can use it in some proofs. Okay, let me go back to the iPad. I'll show you one of my favorite questions, just about like, do you know what the Concoid of Nicometes is? So here, iPad comes back. Okay, here, I'm not going to do that right now. Okay, I'll do it on here. So here's one of my favorite questions about the concoid, just to check, do you know what a concoid is? I'm going to put a point here and connect it to the pole also. And I'm going to name these points A, B, C, D, E. And here is my favorite question. It's more of a question of, do you understand the concept? Here it is. If EB is equal to 7, EB, that's from here to here, if that's 7, and if ED is 2, and if EC is equal to 1, what would the length of EA be? So I really like that question. I like it so much, I'm going to put you into breakout rooms for 3 minutes to think about that. Okay, guys. Hey, everybody. Sorry, I put you in the breakout rooms before. Maybe you got a chance. Wait, is I'm a little confused. Oh, people are coming back. Okay. Were people able to get the answer for this question? Sorry, I know I took down the, I didn't have the
We did not get the
picture and all.
right, yeah.
Sorry about that. Okay, looking at it now though, so everyone's looking at it together now. What do you think? How could you get what EA is? Anyone know what the secret to this question is? What do you really get when they tell you that what EB and ED are? Why is that useful?
You use that to find a difference, to find a distance.
Yes, it's BD that's implied by that question. So BD is 5, 7 minus 2. So what else is 5?
C, AC.
AC. That's right. That's what makes it a concoid. These two line segments from here to here and from here to here will definitely be congruent. And CE was given to you as 1, and that's why the answer to this question was 6. That's kind of like, I really like that question, because if you understand concoid, that question's, you know, really quick and easy, but it's not an easy question because it's hard to get your mind like what it is that's always equal. It's this must equal that. And while I'm at it, if I were to draw like another, line segment from E and just made it until it hit the quadratrix, then this line segment would also be equal to the other two. That's right. If one distance is 5, all the distances have to be 5.
But it'll be 5 from the line of the directrix to the like bell-looking curve all the time, right? Not from the pole.
Not from the pole. That's right.
Okay.
The pole to the concoid is going to be different, but from the point on the directrix to the curve will be the same.
Okay, so would you ever ask us something like that line that's between, what is it? Oh, you didn't label it. So you see the black dot between the black dot and E? Would you ever ask us what is the, like, so yeah, fine, great. So like, let's say you ask us for GE, would we be able to figure that out?
No, only if you also had FE. If you had FE,
Oh, got it, okay.
then you would know FG, so you could subtract them.
Okay. All right, thank you.
Okay, so now let's see, Nina had asked, why do we care about this curve? Well, we care about this curve for the same reason we care about the directrix, the quadratrix, and the spiral of Archimedes. This concoid of Nicometes is something that can be used to trisect the angle. I'm going to put up a diagram for you for a second. This one. And let me tell you what's going on in this picture. These two lines are parallel. I am going to, if you don't mind, I'm going to put numbers here. I'm going to call this 10 and this 5 and this 5. And I'm going to call this angle, this little one, I'm going to call that 25 degrees. And I'm going to tell you something that you wouldn't know already. These are right angles. In a right triangle, if you draw here's the midpoint of the hypotenuse. If you draw this line segment, it will always be the same length as the hypotenuse, as half the hypotenuse. And the reason that's true is because if we stuck a circle around it, they would all be radii of those circles. But I'm just telling you, this is like a theorem from math that's going to come in handy now. Anytime you have a right triangle, if you get the midpoints of the hypotenuse and connect it to the vertex at the right angle, these three line segments will always be equal to each other, which means you could put a 5 here also. There's a lot of lines in this picture. Here's a challenge for you. If DAB is 25 degrees, what's the measure of angle C? What's the measure of angle ABC? Let me say this again. ABD is 25 degrees. That's this. ABD is 25 degrees. Using all this information we have, can you figure out what the measure of angle ABC is? I'm going to mute myself and give you guys time to make some observations about, is there some way of figuring out what angle ABC is?
Oh, these two triangles. No, this must be 65.
Okay, everybody. So what's going on in this picture? I don't see the right answer yet. The trick to this question is there are a lot of isosceles triangles in this picture. And by the way, first question, where's there another 25-degree angle? Because there's another one in this picture, even though it doesn't say it specifically. Where is it though? Name the other 25-degree angle. CED is right. Do you remember from geometry? It's like if it's the letter Z, they call those alternate interior angles. So that's 25 also. Well, you see this triangle here? That's an isosceles triangle. Why? Because this is 5 and this is 5 also. That's only true because of this theorem, that the median drawn to the hypotenuse is always half the hypotenuse. So that gives us another 25 over here. Well, if that's 25, what do you think the size of this angle right here is? So I want to type it in. Yes, that's 50. It's 50 though. It's the exterior angle. So it's equal to 25 plus 25. Oh, wait a second. No wonder why we couldn't get this question. I shouldn't have called that 10. I'm very sorry. The instructions are that DE is twice of BC. So that means BC is just 5, because DE is what's 10. Sorry about that. The given information was, this was not supposed to be 10, it was supposed to be 5. Really sorry about that. Now that that is 5, we have another isosceles triangle. So if this here was 50, this on the other side is 50 also, which makes the answer 75 degrees. There was no way for you to get that because you had a 10 here instead of a 5. Sorry about that. DE was 10, not BC. DE was 10, so DM and ME were both 5, and CB was 5 also. So 50 is this CBD, which makes the entire angle, which includes the 25 and the 50, 75. In other words, it's triple. Or, said another way, ABD is 1/3 of CBD. Well, what does this picture have to do with anything? Back to the GeoGebra page. Okay, what you see in front of you, let me get the chat going. So what I have here is a right triangle, FED, and angle FDE. I could actually change that angle by messing around with this thing. See that? Then I have this mysterious point H, but that point H can move. And it looks like the picture we just did, but look at what happens. If I can move point H, so depending on where H is, angle, what I call angle EDH. EDH is 33.87 now. EDF is 45.61. But if I move H around, angle EDH changes also. Well, if I move H to the perfect spot, and this is very important, the perfect spot, you see HI? HI is currently 1.89. TF is the hypotenuse of the original triangle. That's 2.86. If I move H, move it, 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 stop there. If I move H, listen carefully, if HI changes depending where H is. If I move H to the perfect spot where HI is double DF. Usually HI is not double DF. It's almost never equal to double DF. Double DF is 5.72. As I move H, it's not HF is getting bigger also, but it's HI is the important line segment I'm looking at. If I can move HI to such a spot, if I can move H so that when H connects to D and goes through I, HI ends up double DF. If I do that, I will have the picture that we just saw. Remember the picture we just saw where DF was half the length of IH, but then IH was, there was a midpoint or whatever that showed that the angle was a third. If HI is double DF, then angle EDH will be 1/3 of EDF. And now the question is, what does this all have to do with anything? Get ready. If I have a tool that makes a concoid, now this concoid has a pole, and the pole is going to be point D, and has directrix. The directrix is going to be EF, but like if I made EF, longer, like a full line. And remember I said H has to go somewhere special? Well, that special spot is where the concoid crosses the line, this horizontal line up here. If I move H to that special spot, then, oh, but I forgot to tell you one thing about this concoid. I told you that the pole was D, and I told you that the directrix was FE. But the distance, I don't have that extra line up here, but I made the distance for this concoid double whatever DF is. So the distance is 5.72 for this concoid. And that means if I go anywhere on the concoid, anywhere, and I make a line connected to D, from the directrix to that point will be 5.72. But it will also be true, it's true for every point on the concoid, but it's definitely true for this point also, point G. I better go back to the iPad so I could write some stuff about this. Okay, I promise I will teach this very carefully now. Imagine that this line is 5. And I make a concoid, that thing. Let's say I don't have this line yet. Sorry, I don't have this is what I have so far. And I purposely make my concoid so that the magic number, the distance, is 10. I'm going to put it up here because we usually have like this extra line up here. So, question for you. How long in that case would this blue line segment be? I'm going to just make 2 different colors. How long is that blue line segment? Type it into the chat. It's 10. That's right. Because that's what the distance is. And how long is this other blue line segment? And that's right, it's also 10. And now the big payoff question. How long is that blue line segment? Yes, it's also 10. Well, if that blue line segment is 10, the blue one, not from G all the way to the pole, if that's 10, then we have this situation. Remember I said the midpoint, and this is 5, and that would make whatever this angle is, I'm going to call it X. Let's say we don't know what that angle is. Sorry. Whatever this angle is here, if I call that X, this would be X, this would be 2X, this would be 2X, and the whole angle would be 3X. So what I'm trying to say to you is that if you have the ability to make a concoid of Nicomedes with whatever pole and directrix that you want, and if you choose to make it so that the pole is the vertex of the triangle, the directrix is the opposite side there, and the distance is double whatever the hypotenuse is. And then you make this horizontal line, and wherever it hits that concoid, you make this point here. It will, and then you connect that, point, this point, to D. That angle is guaranteed to be 1/3 of the original angle. And that's why the Concoid of Nicomedes is the final way, the fourth and final way that I'm going to teach you to trisect an angle. They invented this curve as a way of, and there's tools that draw these concoids of Nicomedes. But if you don't have that tool, well, you're not going to be able to trisect an angle with it. But again, the Greeks are saying, okay, we have to cheat a little bit. A protractor is really bad cheating. A quadratrix or a spiral of Archimedes or a concoid of Nicomedes or the Archimedes circle with that extra line, those are all cheating. Yeah, there's 4 ways. There was the Archimedes way with the circle and you had that point F. There was the Archimedes spiral. There was the quadratrix, and now there's the Concoid of Nicomedes. Concoid of Nicomedes is the hardest one. But the main thing I just wanted to show you is that the Greeks invented this exotic curve because if there was a curve that had this special property where the distance from the directrix to the curve is always the same, it would accomplish that. Okay, that does it for trisecting the angle. And this stuff is not, it's not easy. Let's move on to the next impossible problem, which is squaring the circle. Good news for you. You might say, how are we possibly going to do 2 squaring the circles and a doubling the cube? Well, we get to use the same curves. So I don't have to teach you a whole new curve anymore, at least for the next 2. Remember the quadratrix, our friend that gets used for trisecting an angle? Well, it turns out that if you have a quadratrix, the length of this, like foot of it, I called it AJ, will always be 2 times the square side divided by pi. And that's something we're not going to even attempt to prove. I'm just going to tell you, here's a fact for you about the quadratrix. So if this is 10, this length here is 2 times 10 over pi. So that would be like a test question. I would just say, I would cross this out and say, how long is that? And you would just know that it's double the side length over pi. Well, that's going to be really convenient because of the pi here. Might help us get the square the circle, because the problem with squaring the circle, creating something that has area of pi r squared, is that we need something with pi in it, and that would do it. Now, what good is this, having it? Let me show you how, once you have the quadratrix, how you can take this length. Okay, here's what you do. Here's a picture of a circle with radius 10. And you see I have that quadratrix drawn in. This red. And what we do over here on the left there is we make a little right triangle, which has 10 as one of its legs. And the other small leg, see here I have this end point. That is the midpoint of AJ. So my question is, how big is AN in that case? What's the exact length of AN? N is the midpoint of AJ. Well, what's AJ? That was up from the slide before. That's right, half of 20 over pi. And what's that? It's not 20 over pi, though. It's half of 20 over pi, which is best expressed how? What's a good way of expressing half? You can write it as 20 over 2, or even simpler. Oh no, it's, yeah, 20 over 2 pi is one way of doing it. Is that 10? You meaning to say 10 pi or 10 over pi?
No,
Yeah, we need the 10 over pi, because it's not 10 times pi. That would be really big. It's 10 over pi, and that's the length of that little side. Now, they make another line segment whose length is 10 again. That's the radius of the circle. Then we extend this line. We don't know how far exactly. Let's just extend it like a lot. This is a nice right angle here. And the big step is to make a line parallel to, see this hypotenuse here? I make a line parallel to it. Now the big question of the day, well, there's a lot of big questions of the day, but the question I want to know right now is, how long is this red line segment right here? The like base of that big triangle. Everyone take a minute to think about that. Oh, as a hint, these are similar triangles. Remember the Z thing? There's like a Z here. So we do have similar triangles. So let me say it this way: use similar triangles to figure out the exact length of the red line segment. The answer is probably going to have a pi in it. Okay, I see a 10 pi, I see a 20 pi, I see a 40 pi. Similar triangles, I'll use this triangle. So 10 over pi over 10. Now in the big triangle, the missing side is like the longer leg. So that's going to correspond with the 10. And the shorter leg in this other triangle is 10. So I end up with 100 equals 10 over pi times x. So I end up with, if I multiply both sides by pi over 10, I end up with an answer of 10 pi. Ah, yes, good question. Those two triangles side by side, the little one looks like this, 10. And the big one I'll just leave like that. They were already separated, but one was rotated, so it was hard to see like the orientation. Now, if I make these extra two lines, I have a rectangle. So this length here is 10 pi. So what's the area of this rectangle then? Base times height. That's right, 100 pi. And what's the area of the original circle? It is. It's also 100 pi. Let me bring up the GeoGebra page and show you this a little bit. Down here, Archimedes Spiral. Where is it? Constructing roots, golden ratio, pentagon, loon, Quadratrix. Let me go full screen. Okay, so here is the endpoint. Here is the, oh, sorry, I did it a different way here. Forget that. I think the last thing I want to say about this is that point H, as great as it is, sorry, this point, so that we need this length, this BH length at the ultimate spot. But unfortunately, you can't actually get that, because look what happens. When you get to the point where you want to make a 0-degree angle, those two lines, we could get that intersection, but at the end, those two lines like collapse on top of each other. So we're actually not able to, we could get really close to that point, but we can't actually get that point with a compass and a straight edge. So all we need is just that one point. We can get every point on the Quadratrix except that one point, the only point we really need to square the circle. Now, for our purposes, I'm happy if you know this relationship and that you just know that that's like related to, like if I gave you this diagram, and there's a really cool version of the diagram, because now I actually went one step further and actually turned the rectangle into a square using the squaring the rectangle method. So this mainly used similar triangles, but you did need the property that AJ in the quadratrix is always 2 times the radius of the circle divided by pi. That's a very difficult thing to prove and something that we will not. We're just going to take it as some sort of fact. So today what we've done is the quadratrix and used it to trisect an angle. The Concoid of Nicometes and used it to trisect an angle. The quadratrix again, this time using it to square the circle. And I have 2 more things to do for today. The spiral of Archimedes can also be used. Not only is the spiral of Archimedes good for trisecting an angle, but the spiral of Archimedes can also be used to square the circle. And let me show you how that works. I don't know what those 2 things are. I'll get them out of the way. Remember the Archimedes spiral? Let's say that the radius, let's say that the radius is 12. And let's put 120 degree here. I like to have that. Okay, I have a question for you now. How long is this green line segment? And yes, that's right, it is 4. 120 degrees is 1/3 of 360, and 4 is 1/3 of 12. Now, I'm going to draw in 2 more lines. One of them is what's called a tangent line. A tangent line is when you have, like in a circle, like a line that just touches it at one point. Every, curves have like tangent lines, it just touches it. So I'm going to draw in this tangent line. It's hard to draw a tangent line because you might make it like slightly off and it hits the curve again, but as best as you're able to draw a tangent line. I could, like if I was down here, I would draw it kind of like that. If I was over here, I would draw it kind of like that. So depending on where the point is, we can make these tangent lines. But the tangent line that I'm interested in is the one that is tangent at this point right here. Okay, oh wait, hold on one second. Okay, I'm back. Now, there's a 3rd line I'm going to draw. And that line comes from here, and it's going to make it's going to be perpendicular to the green line. And I'm going to create this right triangle with the green. The red is the tangent line, and the blue is that third side. And I'm going to tell you that there is a way to figure out the length of the blue line segment. I'm just going to tell you, this is also something we're not going to prove. That line segment, that blue line segment, will guaranteed to have the same length as, that's guaranteed to have the same length as, if I went from this point, that same point again, and made, if I went from that point and made like an arc of a circle with this as the center, and made it go all the way until it hit the radius. So here's my question for you now. That blue arc that I just drew, what's its exact length? What do you think the exact length? We know the radius of it, and we know this angle here. So how long is the arc? And once we know the arc, that will also be the length of that line segment. How long is that arc? It's like a portion. It doesn't look like a circle because I didn't draw it that well. Oh, well, you know what might help you? How long is this little circle I'm drawing? What's the circumference of this entire circle that has like a blue portion and a red portion? Let's go that way. What would be the circumference of that circle? That's right. The circle would be 8 pi, the entire circle. But what about just the blue piece of that circle? The whole circle's 8 pi. What about just the blue piece? Because you have a blue piece and a purple piece. It's not 4 though, or 4 pi, but it is 8/3 pi, because 8 pi is the whole thing, but it's not the whole thing. It's 1/3 of it because it's 120 degrees over 360 times 8 pi. Which is 8/3 pi. And that will also be the length of this blue line segment. And we know this is another thing we're not proving. I'm just telling you that I promise you those two things will always be the same length, the arc of the circle. If you want a formula, I'll give you one. How about this? The formula is, can I just call this AB, just to call it something? AB is the angle over 360 times 2, because this 8 pi was 2 times pi times 4. But the 4, right, this was 2 times pi times 4, that's where the 8 pi came from. But the 4 was theta over 360 times 12. This is basically, this is the percent of the percent of the circle that the arc is, and this is 2 pi, and this is r. If you were able to say that this green line was 4, because you're like, oh, it's 1/3 of 12. That's basically what this is. That's if you want to do this as a formula. You could combine stuff also. I mean, I don't like to, but I suppose you could say theta over 360 squared times 24 pi. I mean, or times 2 pi. Can I please change this 12 into an r? Because we're trying to get a general formula. If we're calling the theta, let's call the 12 r, that r. That's the radius of the original circle. Let me show you this on the GeoGebra page. Archimedes, Concoid, trisecting angle with a spiral. It must be on the same page as trisecting angle with a spiral. It's not? Here it is. Archimedes spiral to square the circle. Okay, I hope you can see this okay. I can move, if I move this point around, see the tangent line move also? Yeah, let me make this nice and big for you. So what we're saying is that C is somewhere on the quadratrix, on the spiral. And here's the triangle. AI is the length we want to know. Here's the arc. And as you can see, the arc length is 13.13. I did that by finding 2 pi times whatever the length of AC is, because that's the radius of the small circle. But then I multiply that by the angle over 360 again. And these are equal. Check it out when I move this thing around. Sorry, when I move this slider around. These two numbers, see, watch them both, they stay the same. Okay, here comes a question just for you to practice this, because I know this might be kind of confusing. I'm going to make it, let me come back over here and make up a new question for you. A numerical one. I like questions that have nice numerical answers. What if I were to take this point? That means theta is 180 degrees. Here's my radius is still 12. Hold on a second. Where does my right angle go? I got myself confused. Sorry, everyone. Let me just see what I did before. Before I did it at the 120 degree mark. Oh, I connected this. I connected that.
Is class over? I don't know what is happening.
I think he accidentally left his,
Yeah, I completely lost, I can't even see anything.
it says, yeah, hello, it says that you were the host, but he's not listed as a participant anymore.
I was just about to participate.
Well, I am lost, so it's like he went way,
Is class over?
Was it by mistake?
no,
I don't think it's over.
Howsey, I think, Elo, I think you are the host now, so you would have to let him in if he's trying to come back in. I don't know how to do that, so
No.
I don't see anything anymore, I don't.
What, do we want to let him back in?
Good question.
I'm lost.
Let's think about that first. Let's discuss this.
I wouldn't know where to let him in because I don't know. I wouldn't know.
I don't know how this
Go
exactly.
to participants and click next to his name and on the word more, and then you can just make him a co-host.
But he's not in the meeting anymore.
Okay, well, that would be different.
Maybe
Willow,
you can
you're the
invite
host.
him. It says at the bottom, like invite. Maybe you can
Yeah,
invite him
you
back.
could invite him, the host.
The host, that's, yeah,
And then
a go-go, right? Elo?
Yeah,
You?
Tobo, yeah.
Maybe he doesn't want to come back.
No, I think he's probably trying.
That's a lot.
I don't even know what to do.
Is that the reason why we can't see each other?
I don't know, this happens sometimes to me anyway.
Yeah.
Oh, there you guys are. I see you guys.
Now we can see each other, but
But not him.
no, and it doesn't show that he's trying to get in. I'm trying to put in his name.
He's not anymore on the list.
It could be that his device died.
Oh yeah.
This is still recording, right?
It's still
Yeah,
recording.
It
I
is.
don't know what to do. Am I supposed to stop the recording? Oh no, I think it stopped.
No, it looks
No,
like
it's still recording.
But I'm sure he's got to get back in to do something with the recording, which I'm going to want to look at for sure.
We don't just look at us talking to ourselves, right?
Yeah. Can you invite him maybe? Or I don't know how you
My screen looks
see
like.
if he's trying to get in or not.
This is what my screen looks like. Oh, well, that's not it.
That's,
oops.
Now I lost you guys.
that's your Facebook. Obviously.
I can't find you guys.
Well, we can hear you. Okay, well, you're back.
My suggestion is that Steve pick up and continue the class.
Yeah, that's a good idea.
Can't
hear you, Steven.
I was following along, but I don't know where he's going with this. I thought we were trying to square the circle.
can you,
He's the host now. He came back
Yeah.
in.
Hey, everybody, I made it back. My computer
you
had crashed
did make it back.
Oh, wow.
just now. Is there a way, did somebody become host?
I did.
Yeah, hello. Yeah. Yeah,
Um,
that-
If you make me host again, I'll start the, I think it's been recording all along.
it says host next to your name.
Oh, great. Okay, so let me go back to my my screen share. Let's see if this works.
But
Yeah,
I'm
my
hoping the
computer keeps
recording,
making-
you can still do the recording, I hope.
Yeah, I think it's just still recording. I think it's been
still
recording all the way through. Because it says, yeah. Okay, well, sorry about that. So here's where I am. Let me go back to this. I want to see what happens if I choose to make this the point. 12 is still my radius. Here's my tangent line. here's my right angle. And here is that arc that I was talking about. In this case, it's actually a semicircle. So the rule is that this red arc, or I'll say this red line, is gonna always be the same length as this blue arc. But in this case, the blue arc is a semicircle. And here's a good question for you. What is the radius of that semicircle? You can type it into the chat. That blue semicircle, what is its radius?
We're using angle 180, right?
The angle's 180.
Okay.
And I didn't draw the thing that well. It would really be more like that. So what is, and maybe it will help you if I draw in the entire circle, small circle, including this. Maybe that helps you. What's the, yes, 6 pi, because the entire circle, it's basically, it's half, it's 180 over 360 times 2 times pi times 6. I'm going to say 180 over 360. That's 6, because 6 is the radius, because 6 is this line over here, because it was 180 degrees. So this entire circle would be 12 pi, but the blue piece is only half of that, and that's why the answer was 6 pi. Now the area of the entire circle is pi times 12 squared, which is 144 pi. And this line segment, the red one, is 6 pi. And if I were to take the diameter of the circle, which is, I'll make it another color. If I take this line here and make the radius, which is 12, and go out another 12, and then I continue this rectangle, the area of that rectangle, wait, that's 6 times, yeah, 6 would be 6 pi, and this would be 24 pi, which makes it an area of 144 pi. So that, that's how we can use the spiral of Archimedes to square the circle. So we'd make a 180-degree angle. This line would, this line here would be the height of the rectangle. And notice how it's always going to be, it's going to end up being 1/4 the circumference of the circle, 1/4 of 2 pi r, because the circle's circumference is 24 pi, so this is 6 pi, so it's 1/4. But then if you multiply that by 2r, you end up with pi r squared. See, the twos cancel out with the 4 on the bottom, and all that's left is pi r squared. Now the pi is not getting squared because the line on the bottom doesn't have a pi in it. It's just 2 times the radius, which is 2 times 12.
Oh, area of circle.
The circle.
So Professor, to finish the square, you would now square the rectangle?
Yeah, but they wouldn't even bother. They're happy enough to get the rectangle. But yes, you could then go one step further and then square the rectangle. And if you really want to get fancy, instead of going to the 180 points, you go to the 360 point. See what I've just done here? This is the if I do it this way, I use the very last points on the spiral and make this tangent line. In that case, the tangent line, I'll make it a red line. This line would be the same length of the entire circle itself, because it's 360 degrees now. It's the whole circle, and it's the entire radius. So this thing would actually be 2 pi r. By the way, when you make a line segment, that's the circumference of a circle. That's officially called rectifying a circle, just mentioning that. And then this is radius, and this rectangle would also, no, not the rectangle. Sorry, I wouldn't use r. I would use, instead of using the radius, I would go take half of it, take the midpoint, and make this skinny rectangle. So it would be r over 2 would be the width, and 2 pi r would be the height, and that rectangle would also have pi r squared as its area. So there's different ways to make a rectangle that's the same area as the circle. Okay, the last thing is very quick. It should only take about 5 minutes. Doubling the cube. Before we double the cube, let's look at doubling the square. If a square has, if a square is 10 by 10, and I draw the diagonal here, it cuts the square into 2 equal pieces. And if I draw a square on the diagonal, notice how that square has 4 of those pieces, whereas the original square had 2 of them. Of course, the hypotenuse is 10 radical 2. And if you do 10 radical 2 squared, you do get, 200 as the area versus 100, which is the area of the square. But doubling the cube is a lot harder because the volume is 1,000 if it's 10 by 10 by 10. If I make this 20 by 20 by 20, what would its area, its volume be? If I make the second cube double the side length, it would be 8,000. So that's not doubling the cube, right? And this is a very famous problem because they say there was a Greek god there was an altar, and the Greek god wanted a new altar that was bigger than the old, and he wanted it twice as big, so they thought it meant double the sides, but the god did not want a idol that was 8 times the volume. The god just wanted a monument that was double the volume. He was very upset about this. You'd figure if he wants one that's double and he gets one that's 8 times as big, he'd be happy with it, but he was not. He wanted it to be double. So that required getting the side length to be 10 times the cube root of 2. If you do 10 times the cube root of 2, and you cube that, 10 times the cube root of 2 cubed is 200. Cube root of 2 is about 1.26. So the doubling the cube problem is about starting with a line segment and trying to construct a line segment whose length is the original multiplied by the cube root of 2. And they figured out a sneaky way to do this. But it requires a new curve, and that curve is a parabola. So you take a parabola that has equation y equals x squared. That's one of the most famous curves in all of high school math. And on the same graph, you make the graph x equals 2y squared, which is a sideways parabola. And to find the intersection points with algebra, you replace this y, oops. So we had y equals x squared and x equals 2y squared, the sideways parabola. And when you replace this y with x squared, you get x equals 2. Instead of y, I have x squared squared. Huh, something went wrong here. Hold on a second. Make it 2x equals y squared instead, or make it x equals 1/2 y squared. Now when you substitute for this y, this x squared in place of it, you get x equals 1/2 of x squared squared. Multiply both sides by 2. 2x equals x to the 4th, or divide both sides by x and get 2 equals x cubed, which means the x coordinate of the intersection of the two parabolas would be the cube root of 2. And that is actually why parabolas were invented. Parabolas were invented because they needed these curves whose intersection points would get us the cube root of 2. Once you have cube root of 2 as a length of a line segment, you are able to use it to double a cube. I'm not going to go into how that works. I'm just going to say that. And I'm going to finish up by just going back to the GeoGebra page and saying, just showing you a couple of pictures for a second of this situation. Okay. Here was the Archimedes spiral to square the circle page. If I go full screen on that. Remember what I did before? I moved it all the way to the end. Show triangle. Let's shrink that a little bit. Show arc. In this case, the arc is the whole thing. Here's the rectangle. Here's the circle. Same area. You can mess around on these pictures. And that thing I just showed you, the how to get the cube root of 2. This will be our last thing for today. So this is y equals x squared parabola. This is x equals y squared over 2. And you can see the intersection point is cube root of 2 is the x coordinate. So this line segment will be cube root of 2. If instead you make that other parabola x equals y squared over 3, then you can get the cube root of 3 as the x coordinate, and so on, and so on. Okay, I'm gonna go back to the iPad. I'm gonna be done for today. I'll answer some questions. If you look at the homework questions, you'll see that there's only 5 questions. This was a long lesson, but the homework questions, I think, let me glance at them. In fact, let me bring them back up on the screen if people are nervous about that. This was a hard unit, but the homework is pretty easy compared to like how much, so we're basically doing 6, 7, 8, 9, 10, 5 questions. So look, question 5, 6 through 12, so 7 questions. This one asks you to draw some concoid points. This one asks you, like we did, I remember I did that funny question where I asked you about how long is AB. This question asks you about this configuration that was used in the angle trisecting. This question asks you to draw some points on the quadratrix. This question just asks you about the trisecting angle with the quadratrix. This question asks you about the length of EJ. The angle's 150. And this question asks you to find the intersection. You know what, can we change this to x equals
Wait,
y?
Professor, for 11, there's 2 questions. Right up under the picture, it says if EF equals 10, what is the length of JE?
This is for which number?
For number 11, like it changes up the length of EF. Like you see, it says on the top, and then it has another question.
Thank you for saying that. No, there was another question that had a different angle also that I accidentally had that in. There you go.
Okay.
So that was going to be another question where there was a different angle and a different length of EF. But this one, so thanks. There's only one question for 11. Thanks for noticing that. So I know this was a lengthy 2 days, make your head spin. I'm like punch drunk from these 2 days because I'm trying to do it nice and carefully, and it's hard when you don't get to see people's faces and all. But I hope you learned a bunch of stuff about the problems of antiquity. I'm going to stop the recording and I'll stick around to answer some questions.